Welcome back. Today I would like to talk to you a little bit about triple integrals. And let's start with this definition, just the definition of a triple integral over some box B. So remember that in two dimensions, so let me use the bottom of this space to describe this. In two dimensions, we integrate over an interval from A to B, right? In three dimensions, we often integrate over some region, right? Maybe the region is R, and then the function is on top. Like in two dimensions, the function's up here. In three dimensions, the function is some surface up here, right? And then if we went into four dimensions, which is what we're talking about today, is we're taking an integral of a function over three dimensions. So a function that's living over three dimensions is four-dimensional. So the region is going to be something that itself is three-dimensional. So I'm just starting with something like some box that I'm integrating over, right? So I have some three-dimensional object over which there's a function on each point inside of that box, right? So how do you think about a four-dimensional object? First of all, it's hard, okay? So it's not easy to think about something in four dimensions. But a couple ways you could kind of think about it is that over each point in space, like think about a room, and each point in that room you could think about it as having a functional value. So think about the room you're sitting in and think about, let's say for instance, that each point in the room has some color assigned to it, and you could kind of think of that color as a numerical value. So that is some sort of a four-dimensional function where every point in the room is assigned a number, and if you want to think of it as that number representing some color, then that's some sort of a four-dimensional space. And so that's one way to kind of visualize a fourth dimension, is every point inside the box has a functional value. Okay, so we're integrating over an entire three-dimensional region at this point, not just over a line segment and not just over a two-dimensional region. We're integrating over a whole three-dimensional region. Okay, so now that kind of gives us a feeling for what a triple integral is. And before we talked about what's called Fubini's theorem, so let's look at Fubini's theorem for triple integrals. Fubini's theorem says that if f is continuous on the rectangular box B, which is given in three dimensions, so here's my x, here's my y, and here is my z direction. So in the x direction we have a to b, in the y direction I have c to d, and in the z direction I have r to s. Then we get this box and then that's the region in the xy plane, but it's actually raised up r units, and then this is the back of the box, this would be the front of the box that we could see, and then it goes up s more units. And we get this box B. So that entire box that I just drew is what we call B. Then the integral over that box of some function in three variables is I can just write it as a triple integral in x, y, and z, provided that f is continuous on that rectangular box. Okay, so this is very similar to when we did double integrals. I can just break it up and integrate in with respect to x first, or y second, z third. And just like in the case of double integrals, I can change the order of integration if I want to. I'm not going to write down all the different orders of integration that you could use, but it's very similar. So let's do an example of this and just get familiar with doing a triple integral. So, example, let's evaluate the integral, triple integral over b of x, y, z squared dv, where b is the rectangular box given by b is equal to the set of all ordered triples x, y, z such that 0 is less than or equal to x is less than or equal to 1, negative 1 is less than or equal to y is less than or equal to 2, and 0 is less than or equal to z is less than or equal to 3. Okay, so here's my integral and here's my box. That's a nice continuous function, x, y, z squared. So I can set this up as a triple integral. So if I want to evaluate this, and I can evaluate it from 0 to 3 in the z direction, from negative 1 to 2 in the y direction, and from 0 to 1 in the x direction. My function is x, y, z squared. And I said 0 to 1 was the x direction, so this is dx. Negative 1 to 2 was the y direction, so dy. And 0 to 3 was the z direction, so dz. Okay, so now we've set up this integral over this box, and now we just need to go ahead and integrate. So remember, this is just the same as when we did our double integrals. We just take it one step at a time, and anything that isn't the variable that I'm integrating with respect to, I'm just going to treat as a constant. So first I want to look at this integral, and the variable that I'm going to be integrating with respect to is x. So I want to take the antiderivative of x, y, z squared with respect to x. So I still have this integral from 0 to 3. I still have this integral from minus 1 to 2. And then the antiderivative here is going to be 1/2 x squared y z squared. That's going to be evaluated from 0 to 1. And then I still have a dy and a dz on the end. Okay, so let's plug in the 1 and the 0 here. And I get integral from 0 to 3, integral from minus 1 to 2 of, if I plug in 1 for x, I just get a 1/2 yz squared. So 1/2 yz squared minus, if I plug in 0, I get 0, so I'm just done. So this is dy dz. Now, if I really want to, I could take that 1/2 out just to get it out of there. I don't see any particular reason to bring it outside the integral, but I could. So let's go ahead and now look at this integral. Notice after integrating x, the x's are gone. I shouldn't have any x's floating around anymore. If I still had x's at this point, that's not good. Okay, so let's take an antiderivative with respect to the variable y. Okay, so with respect to variable y, I still have the integral from 0 to 3 of. I take the antiderivative of the y, and so I'd get 1/4 y squared z squared evaluated from -1 to 2 dz. All right, so now I need to plug in the 2 and the -1. Let's go ahead and do that. So I'll erase real quick, and I get that this is equal to the integral from 0 to 3 of, I need to plug in the 2, and I get z squared minus, plug in the -1, and I'd get 1/4 of z squared. All of that dz. Okay, so I can simplify that. That's integral from 0 to 3 of 3/4 of a z squared dz. Okay, let's take an antiderivative now with respect to z, and I'd get that this is going to be, I bump the power up to 3, divide by 3, so I get 1/4 z cubed evaluated from 0 to 3. Plug in the 3 cubed is 27, so I get 27/4, minus, plug in 0, I get 0, and so I'm just left with 27/4. What are we talking about here in terms of, like, if I were going to put units on this thing? Well, that's an interesting question. First of all, you'd even have to ask, is this even some sort of like 4-dimensional volume that I'm figuring out here? Is it or is it not? Doesn't even make sense. But I guess it's in units to the 4th if it were. Okay, so you just have to think of this when we're integrating a function over a 3-dimensional region, we're getting some sort of a 4-dimensional object. So just keep that in mind as you're doing this. Okay, so we get 27/4, and now let's try another one. So this time we were integrating over a nice box B. We could also take a triple integral over some region that isn't necessarily a box. Just like in 3 dimensions, we could integrate over a region that isn't necessarily a rectangle, and we would go about it exactly the same way. So let me write down an example for you, and let's see how this works. Okay, so an example. Let's evaluate the triple integral over the region E of z dv, where E is the solid tetrahedron bounded by the 4 planes x equals 0, y equals 0, z equals 0, and x plus y plus z equals 1. All right, so before I start trying to do anything here, first it would be kind of nice just to see what I'm trying to do. So let's draw this region that I'm integrating over. So x equals 0 is just the yz plane. So y equals 0 is just the xz plane, and z equals 0 is just the xy plane. So what we're talking about is we have the 3 planes that are part of my axis system, and then I have this one other plane. But I'd like you to notice something about this one other plane, and that is that there are 3 points that I know are on it, and that's 1, 0, 0, or right here. This is the point 1, 0, 0. 0, 1, 0 would be on it, and 0, 0, 1 would be on it. So if I connect these 3 points, I get the piece of that plane that would be inside the first octant. And notice that it's bounded by the other 3 planes as well. So I have this top piece here, and then I have these sides over here, and this side down here. Okay, so this is kind of a 4-sided, what we call a tetrahedron. Okay, that's the shape that I want to integrate over. So what I'm going to do first is I'm going to say, is there a top plane and is there a bottom plane? Okay, instead of saying, is there a top function and a bottom function, in 3 dimensions I'm going to say, is there a top surface and is there a bottom surface? And the answer is, yeah, there is. And in other words, could I talk about z equals something as the top surface and z equals something else as the bottom? Well, the plane I have right there that is connected by these 3 points, excuse me, I had to sneeze, is the function z equals 1 minus x minus y. And I also have this bottom plane down here, which is z equals 0. So I have a top surface and I have a bottom surface. So I'm going to integrate from the bottom surface, z equals 0, to the top surface, z equals 1 minus x minus y. And the function that's going in the middle here is z. And I know that I'm integrating first with respect to z. But I'm not done. Now I have to go and say, okay, what's the region in the xy plane then that I'm integrating over? So let's look at the xy plane for a second. In the xy plane, I have this region. Here's 1, here's 1. So that's the region if I just look at this thing in the xy plane. I've already taken care of z, so now I'm just asking what are the what am I doing in just the xy plane? I've taken care of the z direction. So in the xy plane, I'm going from a function on top here to a function on the bottom here. So what is this function and what is this function in terms of y? So the top function is what? Well, that's when z equals 0, so I have x plus y equals 1. Okay, so this is x plus y equals 1, otherwise known as y equals 1 minus x. That's that top function. The bottom function here is just y equals 0. So I'm integrating from a bottom function, which is y equals 0, to a top function, which is y equals 1 minus x. That's in the y direction. Then I could say, okay, how am I integrating in the x direction? Well, I've already done 3 dimensions, so surface to surface. Then I need to integrate from function to function. And now I need to integrate from constant in the x direction to constant in the x direction. So from 0 to 1 in the x direction. So this is how you should think of setting up these. First, I'm going to integrate from a top surface to a bottom, okay, or so let me say it right. From a bottom surface to a top surface. then in another direction from a bottom function to a top function, and then in the third direction from a bottom constant to a top constant. Okay, so surface to surface, function to function, constant to constant, where the constant needs to be the one the furthest out in the integration. If you put the constant as the first thing, this is not going to work, okay? The constant needs to be done last. Okay, so I've set up an integral that should get me this triple integral over z integrated over this tetrahedron. Okay, so now that I've got this thing set up, let's go ahead and integrate it. So let me rewrite this on a new sheet. So this integral was integral from 0 to 1, integral from 0 to 1 minus x, integral from 0 to 1 minus x minus y of z dz dy dx. And I'm going to start with the most inside integral. Okay, so let's take an antiderivative of what's inside here. And I get integral from 0 to 1, integral from 0 to 1 minus x. Okay, antiderivative of z with respect to z is 1/2 z squared evaluated from 0 to 1 minus x minus y dy dx. Okay, let's plug things in. If I plug things in, I get integral 0 to 1, integral from 0 to 1 minus x. If I plug in 1 minus x minus y for z, I get 1/2 of 1 minus x minus y quantity squared. And then if I plug in the 0, I just get 0. So this is going to be dy dx. All right. Now, I could, at this point, square this out. Or I could just think about it for a second, and I could say, in terms of y, what's really going on here? That if I take an antiderivative here, the only real change that I'm going to see is I'm going to be basically kind of multiplying by a -1 and maybe a 1/3. But if it's helpful, we could multiply this out, square it out, and then do it that way. So do whatever feels best for you. I am going to take an antiderivative just kind of in my head a little bit, and then I'm going to check to make sure that what I said my antiderivative is actually right. But like I said, if in doubt, multiply this thing out, square it out, and see what you get. So, oh, I'm sorry. Let's go back a minute. So I'm going 0 to 1, and then I want to take an antiderivative here. So antiderivative, I believe we'll get -1/6 times 1 minus x minus y cubed evaluated from 0 to 1 minus x dx. And now let's see, do we believe that this is actually true? So I kind of did this in my head. Do we believe it? So if I took the derivative of this thing, the 3 would come down and I'd get -1/2. And then I'd multiply by a -1, which would give me +1/2, and it would be perfect. So this is the antiderivative. And now I want to evaluate it from 0 to 1 minus x. And remember, I'm plugging in for y here. Okay, so I get integral from 0 to 1 of -1/6 times 1 minus x. I'm plugging in for y, so I get -1 minus x. Okay. Minus plugging in 0, right? So if I plug in 0, I get minus 1/6. 1 minus x minus 0, which is just 1 minus x. Okay, and this needed a cubed, and this needs a cubed dx. Okay, so what's inside right here? I get 1 minus 1, which is 0, and I get minus x plus x, which is 0. So this whole term right here is just 0. So what am I left with? I get integral from 0 to 1 of minus 1/6, which is 1/6, times 1 minus x quantity cubed dx. And now we can do a similar kind of antiderivative here. And so our antiderivative should be, let's see, we are going to divide by 4 and multiply by -1 to give us -1 over 24. 1 minus x to the 4th, evaluated from 0 to 1. Okay. And then I plug in, if I plug in a 1, I get 0. Minus, if I plug in 0, I get -1 over 24. And minus 1 over 24 is just 1 over 24. And that's my answer. Okay, so the hardest part of these problems is definitely setting it up. The antiderivatives, we know how to take antiderivatives. We can get through all of that. The tricky part is setting it up and remembering we need to integrate from surface to surface, then from function to function, and then from constant to constant. Okay, let's do one more just to get a little bit more practice. So, last example, let's evaluate the triple integral over e of the square root of x squared plus z squared dv, where e is the region bounded by the paraboloid, y is equal to x squared plus z squared, and the plane y is equal to 4. Okay, so the first thing that I should always do when I'm trying to do one of these problems is I should graph this thing and get a feel for what it's looking like if possible. So let's start out by drawing our three-dimensional axes. And I want a region that's bounded by the paraboloid y equals x squared plus z squared. But that looks sort of like a parabola in this direction and a parabola in the xy plane. So, okay. And then out here at y equals 4, we have a plane cutting it off. So cut that paraboloid at y equals 4, and I get this region in here, right? Kind of like half of a football or something like this. A football cut in half, or maybe like a chopped watermelon might be another way of thinking about this region. So you've got this like half watermelon region, and you'd like to integrate this function over that half watermelon. Okay, so the first thing that I need to think about is I'm integrating this thing from a surface to a surface. So I need a top surface and I need a bottom surface. In my last example, the top surface, I wanted it to start integrating in the z direction because I had a very clear z surface on the top and the bottom. In this case, it's not so good. I don't want to solve this for z, but it's already solved for y, so maybe the question I should ask is there an obvious top y surface and bottom y surface? And the answer is yes. The top y surface is sitting right here. It's the plane y equals 4. And the bottom y surface is here. It's the paraboloid. So when I'm setting this up, the first thing I see is I want to integrate from the bottom surface, which is x squared plus z squared, or the paraboloid, to the top surface, which is y equals 4, of this function, square root of x squared plus z squared, d, well, what direction is that in? These are both y equals surfaces, so dy. But now I need to integrate from a function to a function in which plane? Well, y is taken care of, so we need to look at the xz plane. And what is this function sitting over in the xz plane? Actually, I'm going to move to a different. In the xz plane, if I project this thing down onto the xz plane, here's x, let's say, and here's z, it's just a circle, correct? It's a circle in the xz plane if you think about what is the region in the xz plane that this surface is sitting over. And what is the radius of that? Let's see, at y equals 4, that means that's radius 2. Okay? Now, this is a circle, and so it does have a top function, it does have a bottom function, but circles are so much nicer if we're looking at the circle in polar coordinates, correct? So what if I thought about this in terms of polar instead of thinking about this in terms of rectangular? So let's see what we've got right now. So far, I've got an integral in 2 dimensions over this, let's call this region capital D. I want to integrate over D of the integral from x squared plus z squared to 4 of the square root of x squared plus z squared dy, and then I need to integrate over that region, the area of this region, D, right? Okay, so let's just do this inner integral and then kind of deal with the D portion in a second. So if I did that inner integral, I'm still integrating over D. In terms of y, this is just square root of x squared plus z squared, y evaluated from x squared plus z squared to 4 dA. Let's plug it in, and I get double integral over d of, if I plug in 4 for y, I get 4 square root x squared plus y squared. Oh, I'm sorry, z squared. And then I get minus, if I plug in x squared plus z squared for y, then I'll get x squared plus z squared. This is already to the 1/2, and I'm raising it to, multiplying it by x squared plus z squared, which will give me x squared plus z squared to the 3/2 dA. Okay, so now I'm ready to integrate with respect to d, but I said d might work better for me if I were working in polar. So x squared plus z squared in the xz plane, that is my r. And then, so what I'm going to do is I'm going to replace x squared plus z squared with r. So now let's see what we've got here. If I'm integrating this over this region that is just this circle of radius 2, then what are my r and my theta being integrated over? Typically, we would say that dA is going to be the r first and the theta second. What goes on the inside? Well, this is 4 times the square root of r squared. And minus, this is r squared raised to the 3/2 power. But then I need to remember, if I'm converting over to polar, I need to throw an additional r in there. Okay, now I need to say, and what am I integrating to and from? In the r direction, we're starting at 0, and we're integrating out to 2 in any direction. So 0 to 2. And theta starts at 0, and then we integrate all the way around until it gets back to 2 pi. So we're integrating from 0 to 2 in the r direction, 0 to 2 pi in the over theta. Okay, so now let's multiply this out and get this into a little bit better form. We've got 0 to 2 pi. We've got integral from 0 to 2. And then what do we have here? This is 4r minus, this is r squared to the 3/2, which is the same as r cubed dr d theta. Okay. So now I am, I'm sorry, something went horribly wrong, and that is that I forgot an r, right? I forgot to multiply everything by r, but this r kind of fell off, but it's right here. And so let's rewrite it one more time here. This is integral 0 to 2 pi. This is 0. Integral from 0 to 2 of 4r squared minus r to the 4th dr d theta. Okay, now we're all set up, ready to go. Now I can integrate this thing with respect to r. Okay, so if I integrate with respect to r, I get integral from 0 to 2 pi. Antiderivative with respect to r is going to give me 4/3 r cubed minus 1/5 r to the 5th evaluated from 0 to 2 d theta. Okay, let's plug things in. If I do, I get integral 0 to 2 pi. Plugging in the 2, I get 2 cubed, which is 8. 8 times 4 is 32 over 3. Minus, plug in 2. 2 to the 5th is 32, so it's minus 32 over 5. If I plug in 0, I get 0, so that's just it. D theta. Okay. So I guess I could combine those two. If I wanted to get a common denominator for 3 and 5, I suppose it's 15. So 32 times 5 is 160. So I have 160 over 15. And then if I wanted to multiply 32 times 3, suppose that's 96 over 15 d theta. And so I can rewrite this as integral from 0 to 2 pi of, let's see, I guess I get 160 minus 96, which is 64 over 15 d theta. Antiderivative is just 64 over 15 theta, evaluated from 0 to 2 pi. Let's plug things in, and I get 64 over 15 times 2 pi minus 0, which gives me 64 times 2, of course, is 128 pi divided by 15. And we're done. So I wanted to show you one where we could do a triple integral using polar, or we could do a triple integral using rectangular. You have to just decide in each case which is going to work out better for you in that situation. Okay, time for some homework.